So what exactly is the phi scale? Mathematically, the grain size in phi is equal to the logarithm with a base 2 of the diameter of the grain size in millimeters, the median diameter of the grain size. I know it's a kind of a weird logarithm to have a base 2 log, but that's the definition defined by sedimentologists to encompass a very large size range of grain sizes of sediment that they were looking at, and to be able to physically model them with a much more accessible scale. Okay, so how do you go about figuring out from grain size and sorting what type of deposit you're looking at in terms of the volcanic deposits, and in particular the Bishop Tuff? So the first thing you would do is when you're out in the field, you would collect giant bags full of material, just a big sample of the bulk. We call it a bulk sample because we just collect everything. It's like just collect a massive sample of each layer that you're looking at. You'd go back to the lab. Sometimes you can do this in the field, and you'd run your samples through a set of standard sedimentology sized sieves with meshes that jive with the phi scale and the phi range of grain sizes that you're interested in. So in the in-person version of this class, we do this exercise in the lab with these samples from the Bishop Tuff, but in the online class, you're going to be given the data provided for you from two different class sessions where the students did the grain size through sieving exercise from the Bishop Tuff data. You tabulate the grain size data by coming up with a plot of cumulative weight percent of each size class as a function of the grain size in phi units. So an example of the cumulative curve is shown here on the right from Cass and Wright. So this is from the appendix reading that you'll do that accompanies this module. This shows on the left-hand side scale a cumulative weight percent coarser than the size, plotted as a function of the grain diameter. The phi scale is given on the top and the millimeter scale is given on the bottom here. And you can see that if you look at this cumulative weight percent across the different grain sizes shown, you get curves of increasing cumulative weight percent as a function of, in this case, decreasing grain size. You'll use the cumulative curve to derive Inman parameters of median grain size and graphical standard deviation, which is a measure of how well sorted the deposit is. The median grain size is called MD sub phi. This is the phi grain size at the 50th percentile. So on this chart, you can read that off by going to the 50th percentile and coming over to the right, and you're going to hit the first curve and you're going to say, okay, so the median grain size from this cumulative weight percent plot for the first curve is down here. It's about 0.5 minus 0.5 phi, and so on. Sigma phi is the graphical standard deviation. It's a measure of the spread in the sizes. So sigma phi is equal to the phi at the 84th percentile minus phi at the 16th percentile divided by 2. So in order to calculate that graphical standard deviation, you would go to the 84th percentile, you'd come on over here, and you'd say, okay, for this curve, that's a phi of about 1. The 16th percentile for this curve is a phi of about minus 2.5. And you do the subtraction here, phi 84 minus phi 16 divided by 2, and that gives you the sigma phi. So this slide is going to make a much better sense after you've read the appendix number 1 from Cass and Wright that is required reading for this homework assignment. So if you haven't read that yet, go back, stop the lecture and read that now, and then join back in again when you've finished. All of this will make a lot more sense after you've read the appendix. Okay, so histograms show the relative distribution of each deposit size according to grain size. This is another really important factor of doing this granulometry exercise for physical volcanology. So a histogram is, just in review, most of you should have had this already in a variety of math classes. It's basically a plot of the weight percent in each size class. So the size classes are divided up and plotted along the x-axis. In this case, going from minus 4 phi to 4 phi. And weight percent in each of the size classes here, which are divided by 1 phi increments, are shown plotted along the y-axis here from 0 to 30%. So the weight percent in each size class is shown here. This histogram for a fall deposit gives you a measure of how well sorted and what the average size is, or the median size is, of your deposit. You can see most of the fall deposit clusters around 0 phi here, but there is a spread that tails off towards 4 phi and minus 4 phi. Pyroclastic flow deposit, you can see, does not have quite the peak. It's not quite, it's basically poorly sorted. It means that there's a more even distribution of weight percent of each grain size in each size class, all the way across the size range. A surge deposit down here on the lower left is very interesting. It's kind of in between the two. It has kind of a peak here in the fine grain sizes. It's skewed towards all fine grain sizes, but it's also got more spread than you would expect from a fall deposit. So histograms are an important visual and quantitative tool to estimate median grain size and sorting, along with the Inman parameters we talked about. So how do we figure all this out? Okay, so you can compare median diameter of your grain size, estimated through granulometry, with the graphical standard deviation by comparing with known fields from prior eruptions. So from Cass and Wright in the appendix, you'll see these two classification plots. On the top, you've got the Inman sorting parameter, sigma phi, plotted on the y-axis as a function of median grain size, plotted along the x, and you'll see some different fields here. So the field of pyroclastic fall deposits is shown here by the stippled curve along the bottom. The field of pyroclastic flow deposits is shown up here by the hatched, cross-hatched, or it's diagonal hatched field here. So one thing I'd like you to note is that there are some separations. Pyroclastic flow deposits tend to be much less well sorted. They have a higher Inman sorting coefficient. That means they're decreased sorting. There's a bigger spread in the class sizes from the granulometry than the fall deposits, which tend to be pretty uniform. Fall deposits will fall across all grain size ranges though, but individual deposits are well sorted. They have a low graphical standard deviation. But there's overlap. So what do you do with this region in between here? This is a region where you could have both a fall or a flow deposit. You might not be certain based on the granulometry. Down on the bottom here, surge deposits, you can see, actually lie kind of in a subset range here in between the fall and flow deposits. So fall deposits are better sorted. They typically have a graphical standard deviation less than 2. Fall deposits can span a wider range of median grain sizes, from very coarse to very fine grained, but each individual deposit is well sorted. Flow deposits are typically poorly sorted. They have a graphical standard deviation that's greater than 2. Flow deposits tend to cluster at finer grain sizes. They tend to be up in the 0 to 2 to 4 phi range, or minus 2 to 4 phi range. Surge deposits tend to plot on the cusp in between the fall and flow fields where they overlap. So that gives you an idea of how robust this classification system is. All right, so for this problem set, your task is going to be used to use granulometry to test field hypotheses about the Bishop Quarry Site Bishop Tuff deposits. The first hypothesis is the base of the flow, unit A, or base of the outcrop, unit A, is represented by fall deposits. So these are Plinian fall deposits that came out before the pyroclastic flows flowed down the valley. The middle outcrop here is layered and cross-bedded. So my first thought would be that could be a surge deposit, a series of surge deposits. So that's my hypothesis. The top is poorly sorted and massive. It doesn't have any layering, but it's not sorted like a fall deposit. So I think that might be a pyroclastic flow. Okay, so the base of the deposits, again, we're going to go through these characteristics. Well sorted, most of the grains are about the same size, not much fine ash. It's very close to the volcano. It's not layered. I think that might be a fall deposit. The midsection, again, is stratified, layered, and cross-bedded layers signify a change in the depositional mechanism. My hypothesis here is that it could be a surge deposit. It's cross-bedded and layered, it has flow structure, it looks like it flowed. The top section is fines rich, but with large floating pummices. It's poorly sorted and massive. Some layering, there could be finer and coarser grain sizes, but they're all very poorly sorted. So I think that's a pyroclastic flow deposit. But, okay, so the following provides just some more field data that I took from my field notebooks that describe what's going on in here. So just read through this data as you need throughout your, while you're doing your homework set. Sample A is moderately well sorted, class supported, fines depleted, has pumice class between 1 and 3 centimeters in size, medium to coarse ash size, finer fraction. Sample B is moderately well sorted, class supported, fines depleted, pumice between 1 and 3 centimeters in size, medium to coarse ash size, finer fraction. So these are the samples that I collected for this exercise. So my hypothesis here is that the basal layers represent Plinian fall deposits from early in the eruption sequence. Okay, but the middle and top are different. Sample C, class supported with pumice 3 to 5 centimeters in size, medium to coarse ash filling in between cracks and crevices. It has dark fragments in it and some layering is observed. Sample D is cross-bedded, individual layers of 1 to 2.5 centimeters thick. Sample E was fines depleted, has individual layers that are 5 centimeters thick, and crossbeds have concentrations of coarser grain class, 0.5 to 1 centimeter size pumice. Okay, so this is the second unit where it's layered, and these are the sample descriptions that go along with the samples that were sieved. The top, we have sample F and sample G. Sample F is the base of the massive, poorly sorted unit. It contains fines, rich layers in it, but it's massive and poorly sorted. Sample G is the same thing, but it's a coarser grained layer. Okay, so my hypothesis here is the upper deposits are pyroclastic flow deposits that didn't have any post-eruption modifications. Samples in the intermediate range, though, the layered and cross-bedded section, I had two hypotheses. The first is that these are layered surge deposits, so that means that this was a base surge that came out of the volcano before the massive pyroclastic flows came down and deposited with all of the bed forms you expect from a surge deposit, the layering, the cross-bedding. There's another hypothesis here, though. They could be reworked Plinian fall deposits by wind. So the way this works is you have fall deposits that were deposited, like the basal layers, and before the pyroclastic flow reaches this area, it's pushing a huge amount of wind in front of it, and that wind actually picks up and reworks those fall deposits and lays them down in layered and cross-bedded format. Just basically like Aeolian dunes. So those are two hypotheses, and you're going to use granulometry data to try to answer those questions. Okay, in summary, first I'd like you to read through the PowerPoint slides in detail, especially the sample descriptions. You'll be given granulometry data from a subset of those samples for this exercise. Then read through the homework assignment Word document in detail before getting started. I really want you to have an idea of what you're going to be expected to do before you get started so you don't miss anything. You don't forget to do a part of the work. Just read through it step by step so you have a whole lay of the land and you know what's expected of you. Locate your statistical graph paper. I have this as a PDF file in Blackboard that you can print out. It works best to draw directly on this graph paper, so I suggest printing it or having it printed and then using colored pencils in order to draw your graphs that you'll be asked to draw. You're going to need to upload copies of your work, so you can take a photo of your graph paper with a smartphone to upload it with the rest of your work in Blackboard. And if you need help with this, just ask me. I'm happy to help. Definitely read Cass and Wright Appendix 1 before you get started. The PDF file is provided for you in Blackboard. It contains all the information you need for the background about the methods you will be using. And if you have any questions, please ask. All right, get to work and have fun.